Hello, 10 triple. Today we are going to be looking at something called specific heat capacity and something called specific latent heat. Latent meaning hidden. So first off, I'd like you to write down the title, specific heat capacity, and then we're going to read through this. Mr. Dog, he's saying that a kettle uses electric energy to heat up water. Yeah, I'd agree with that. And Britney Spears has said, that's right, Mr. Dog. And did they also know that water can store a lot of heat energy? It can. It's got a high specific heat capacity. Okay. That is also correct, Britters. A-star, well done. What all my fans need to know and write down is the following. So you've written down the title, specific heat capacity. I'd like you to write down this bottom paragraph. That's the only thing else that you need to write down. Now, what does it mean? The specific heat capacity of a material is the amount of energy in joules needed to raise the temperature of 1 kilogram of that material by 1 degrees centigrade. Now the units, and you will need to know these units for specific heat capacity, are joules per kilogram degrees C. So remember, the only thing that you need to write down off this page is the title and this lower box here. Metals tend to have relatively low specific heat capacities. In other words, you don't need very much energy to heat it up, whereas non-metals have a higher specific heat capacity. You've got to put in more energy to heat up those substances. Now, the equation that will always be given to you is the following. Now, what do these symbols mean? Q is the amount of energy gained or lost. That's going to be in joules. M is the mass. That's going to be in kilograms. This triangle T, delta T, stands for the change in temperature. And that will be in degrees C. And then C itself, that is your specific heat capacity, and you should know that the units are joules per kilogram degrees C. Now, let's go through a couple of examples, and it should start to make some sense then. So you should have handouts 27, 28, 30 and 30A. If you don't have those, let me know and I'll send them out to you. So let's have a look at this question now. A kettle contains 1.5 kilograms of water. It's at 18 degrees. How much energy is needed to boil the water? Well, energy used is given by the symbol Q, so we just write down the equation. Q is what we're after. M times C times the change in temperature. Now, the mass we've been given, 1.5 kilograms. Multiply that by the specific heat capacity of water. There it is, 4,200. And then multiply that by the change in temperature. Well, if it boils, it goes to 100 degrees. It started off at 18, So the change in temperature is 82 degrees C. So 82 degrees C. Times those three numbers together, obs using a calculator, and I get 516,600 joules, or I could convert that into kilojoules. 516.6 little k big J. Easy. Okay, question 2. What energy transfer, so we're trying to work out energy used again, is needed to heat a 500 gram aluminium pan containing 200 grams of cooking oil from A to B temperature? So we've got two calculations to do. We've got one for the aluminium, and then we got one for the cooking oil. And then you just add them together. So let's do the aluminium first. We've got an equation, Q equals MC, change in temperature. Now, what was the mass of the aluminium? It was 500 grams. You got to put that into kilograms. You divide it by 1,000, 0.5. Then you get the specific heat capacity of aluminium. That's over there, 880. Multiply that by the change in temperature. It started at 20 degrees. It went up to 170 degrees. The change is 150 degrees C. Nice, easy calculation. $66,000 joules. But of course, we also heated up the cooking oil. So we do exactly the same equation again. Put in the values. So the mass of the cooking oil, 200 grams, 0.2 kilograms, times by the specific heat capacity, it's about 1,200. I got that from the handout. And then you times it by the change in temperature. It's the same as it was for the aluminium, 150 degrees C. $36,000 joules. Then all you do is you add those two values together. Total energy transfer equals 66,000 add 36,000 gives us 102,000, and we're looking at energy transfer. It's the amount of joules. Okay. Now we've got 5 questions here. Don't pick 2. I want all these 5 questions done. If you haven't got this in the handout, you're going to have to write down the questions. I'm going to try a tricksy one here. I'm going to have a go at question 2 because it does involve rearranging the equation. So let's have a go at question 2. Up here, we've got this equation, Q equals MC, change in temperature. Now I can see straight away that it's asking us to calculate the temperature change. So what I've got to do now is put the change in temperature on its own. Okay. The change in temperature is going to be on its own. Now what I do is I leave the Q where it is, and these two figures here M times C, they go down underneath here. So it's going to be Q divided by MC. Okay, that is the rearranged equation. So change in temperature is Q, the amount of energy. So the amount of energy here is in joules. I can see that straight away. It's 90,000. And that is divided by the mass of the brick. I can see that here. It's 2.35 kilograms times by the specific heat capacity of the brick. That's there, 840. So the change in temperature is that. So the temperature change equals just a nice simple calculation now. And you get quite a long answer now, but to one decimal place, it's 45.6 degrees C. That is the temperature change. I want you to have a go at questions 1 to 5. I will add in the answers, but I want you to have a go first. Okay, so here are the answers to questions 1 to 5. You need to make sure that in all of these calculations, you have not only written, number 1, the equation, number 2, you've shown all your workings, and then I want the answer plus the right units. Now, once you've done questions 1 to 5, that is the end of lesson 1. I want you to stop, take a break, and then replay the video in about 10, 15, 20 minutes time. So take a break and I'll see you in a second. Okay, 10 triple, this is the second lesson for today. We're going to be looking at something called specific latent heat. Have a read through this. It might not make any sense. Don't worry about it. Right? Just have a read through it. We've got the specific latent heat of fusion. That relates to melting or freezing. And then the specific latent heat of vaporization, when we boil or condense something. Okay? Don't worry about it at the moment. Now, we can see here solid, liquid, gas. During a change of state, so yes, during a change of state, we get a change in the energy within the particles and the energy required to hold the particles together, right? Here's the big one now, right? I definitely highlight this. When materials change state, you know, they go from solid to a liquid, the temperature of the material stays the same. So if the solid was, I don't know, 20 degrees C and it changes into a liquid, it stays at 20 degrees C, right? This happens because heat energy is being used to make or break the bonds between the particles. So you're putting in energy, you're putting in heat energy, but it's not causing the substance to heat up. What it's doing is it's changing the state from one form to another. It's making or breaking bonds between the particles. It's not increasing in temperature. That's the big thing, right? So even though the overall energy increases, the temperature stays the same. So let's have a look at this graph here. You can see we've got a solid here that's heating up, and then the liquid here. But when it changes state, the temperature stays the same, and it stays at 0 degrees here. And so let's just have a look at this example just a little bit further on. This section is all to do with a liquid heating up. This is the vapor heating up, but when it changes state, when it boils, when it changes from a liquid into a gas, a vapor, notice that the temperature stays the same. Let's give this a go now. Let's go through a couple of questions. Here's question 1. So here's a question. The meaning of the word latent, it means hidden. In terms of latent heat, it suggests that heat does something that is hidden. Now, what happens when you get a change of state from like a solid to a liquid, what happens is some of the heat is not used to actually raise the temperature of the substance. It is used to break bonds. Okay, so if we have a look down here, we've got a solid here with bonds, and some of those bonds are snipped. There's not so many bonds now. Okay, so we got a situation where some of the heat energy is used to cut the bonds. So we've gone from, this is a solid, into a liquid. Now, the value for the specific latent heat of fusion for ice is this value. That's quite small because we're only cutting a couple of the bonds, whereas the value for the specific latent heat of vaporization of water is much, much, much bigger. And that is because if you want to go from a liquid to a gas, you've got to snip all of those bonds. All of those gas particles, they're free now. There's no like bonds between them. So that takes a lot more energy. Suggest why the word latent is used and account for the difference in the two values. So this is your answer here. Latent is used because the energy that goes in does not raise the temperature of the substance, but merely goes to enable the change of state to take place. In other words, we are either making or breaking bonds between particles. And that's what it's going into. It's going into breaking bonds between molecules. Okay? Now, in the case of fusion, and remember, the fusion is the change of state between a solid and a liquid. There are only a small number of bonds are broken. Now, we've seen that already. There's only a small number of bonds broken between a solid and a liquid. Whereas the latent heat of vaporization refers to a liquid changing to a gas, and there's always a lot more bonds being broken, and so the value is always much larger. because the number of bonds being broken is much larger. Now, let's have a go at question 2. How much energy is needed to raise the temperature of 3 kilograms of ice from -10 to water at 40 degrees C? We've got 3 changes here. We are heating up ice along here. Then what we are doing is we are changing the ice into water. That happens along here. And then we have a situation where we've got water now and we're heating up to about 40 degrees C. So, let's have a look at these questions. The first section is number 1. We're going from -10 degrees C to 0 degrees C, and that is ice. That is this section on the graph that I've coloured in. Okay? Now, in order to get that figure, energy equals mass times specific heat capacity times change in temperature, and that equals, we've got 3 kilograms of it. The specific heat capacity of ice is 2,108. Times that by, well, we're going from -10 to 0, so the change is 10. And so we get an answer of, then we go on to, we're actually going to change the ice into water. The equation that we need is, I'm just going to go up again. This is the equation that we need. There it is, Q equals ml. This relates to this section of the graph. It's the yellow bit. When we're going from ice to liquid water. And so we need a certain amount of energy. Remember, the temperature is not changing. All we're doing here is making or breaking bonds. In this case, we're going from ice to water. We're breaking bonds. So what was the mass of the ice? 3 times by the specific latent heat of fusion. Remember, fusion is to do with solids to liquids or vice versa. So it's 3 times that value there, which gives us just colour coding these up. And then we've got water now. And the water started off at 0 degrees and then went up to 40 degrees C. Remember, that was water. And so we're just going to find out how much energy is needed to raise 3 kilograms of it by a change in temperature of 40 degrees. And the mass was 3 times by the specific heat capacity for water, 4,200, times by the change in temperature was 40. We get this value here. That relates to this part of the graph, and when you add those 3 values up, the blue, the yellow and the pink value, the total equals Don't forget the units, joules. Final question today. We've got a recycling company. It aims to melt 500 kilograms of aluminium in 1 hour. The aluminium is at a start temperature of 20 degrees C and is to be completely melted at 660 degrees C in a furnace with a power of 87 kilowatts. Use equations from page 2, so that's the front inside cover of your exam, and the information below to determine whether it is possible to meet that deadline. Now, not easy, I've got to say this now, but let's work out the amount of, let's have a look at the furnace. And we've got an equation that is energy is power times time. Now we've got the power and we've got the time. So we can work out the amount of energy the furnace generates. The power is 87 kilowatts, but power is measured in watts. So you times that by 1,000 and you get the power is 87,000 watts. Now the time is in hours. Apologies. The time is in seconds. So energy is power in watts times the time in seconds. Now it's on for 1 hour. You've got to convert the hour into seconds. So 60 minutes in an hour, 60 seconds in a minute. And you get this answer here once you multiply all three numbers together. That is the amount of energy generated by the furnace. Now, is that enough to completely melt all of that aluminium from 20 degrees C up to 660? Well, let's find out. The energy needed to melt the aluminium. Okay. First off, we've got to, number one, convert aluminium from solid into a liquid. That is the specific latent heat equation, Q equals mL, and that equals the mass is 500 multiplied by the specific latent heat of fusion, and that gives us 2 times 10 to the 8 joules. That is the amount of energy needed to melt the solid aluminium into a liquid. Now we have to deal with the change in temperature, of course. Okay. This is the increase in temperature of said aluminium, and that equation is the specific heat capacity equation. So the mass is 500, the specific heat capacity of the aluminium is 900, and the change in temperature is, well, it started at 20 degrees, you've got to get it up to 660 degrees. So the change in temperature is 640. That gives us a value of 2.88 times 10 to the 8 joules. What we do now is we have to add these two values together, and you get a total of 4.88 times 10 to the 8 joules. So in order to melt 500 kilograms of aluminium and raise its temperature through 640 degrees C, you need this amount of energy. However, the amount of energy that the furnace generates in that 1 hour is less. So your answer is no. No, it's not possible to meet that deadline. Either the furnace would, well, you'd have to increase the power output of the furnace, or the furnace would have to be on for longer. It's that simple. That will end our double lesson today. Well done.